Hi guys, today I want to talk about model validation, specifically cross-validation and grid search. Cross-validation has many strategies and one of the most famous is KFold cross-validation. In KFold, all the data gets a chance to be tested one time. So why do we use cross-validation? Imagine you bring your dataset and run the algorithm 10 times with cross-validation. If across those 10 iterations, the validation score is very close to the training score. Let's say the difference is less than 5, 6, 7%. And in more than 7 out of 10 runs, the model is not overfitting. That means your data is pretty good. But if the model is overfitting too much, for example, your training score is 85%, but validation score drops to 50%, then it means overfitting is happening too often. And you need to change your validation strategy. Cross-validation is one of the ways we can solve this issue. So let's go to the code. And first, I import cross-val predict and cross-val score from model selection in scikit-learn. I'm going to use a decision tree classifier with some hyperparameters that are not tuned yet. Tuning is something we will do later with optimization algorithms. Right now, I don't know whether the best choice will be max step or maybe something else, or whether the best split criterion will be Gini, entropy, or others. Another important thing here is class balance. In this example, my dataset is already balanced, but if your dataset is not balanced, then you need to handle it. The function cross-val score takes several arguments. The first one is the estimator. In this case, I chose a decision tree. Then it takes x and y, which we defined before in previous videos. And CV is the number of folds, and scoring is the evaluation metric. When I printed the results, as you can see, that the data was split into 10 parts. So we get the accuracy for each of the 10 trees. And then we can calculate the mean accuracy across all folds. And you can see our performance is about 74%. There is another way we can do cross-validation using KFold directly. This has some advantages. For example, notice the argument shuffle equal true. Shuffling randomly changes the order of the rows in the dataset, which helps avoid negative effects from how the data was originally ordered. For example, you have a medical case, which the data customized by age. In this way, if you don't shuffling, you may choose, for example, age 10 to 40 to create model and test on people who has more than 50 years old. That could easily lead to overfitting. By shuffling, we mix up the rows, so each fold gets a more balanced representation of the dataset. And the argument random state controls the shuffling. If you choose a fixed number for a random state, then you will always get the same shuffling result, which makes your experiment reproducible. Next, I use cross-val predict to compare the prediction with the real values. Here, the confusion matrix showed results. These are the real values, meaning some of the first row is equal 352 belong to class 0, and the second is 245, which means belong to class 1. Now, let's talk about the hyperparameters tuning, which is very important. We know the hyperparameters of our decision tree, like criterion, max tip, mean sample split, and mean sample leaf. And also there are other hyperparameters, but the importance is these parameters. But the best value are not obvious from these hyperparameters. That's where fine-tuning comes in. One of the usual methods in GridSearch basically works like a for loop. It tries every possible combination of the parameters you give it, and then tells you which one worked best. So I import GridSearchCV. Now I define my decision tree, and then I define the parameter grid. This is basically the environment where the grid search will search for the best combination. Grid search has a few key arguments. The first one is the estimator. Here I chose decision tree. The second is param, which is included in the dictionary of hyperparameters, as you can see. Then CV is the number of folds, and scoring defines the performance of 10 trees. After this, we did the step fitting. We can also check runtime in Colab or other notebooks by using %time. And you can see here you have CPU time and wall time, which is around 12. For finding the best combination of hyperparameters, we can use best param, gs.best param. You can see the best parameters here is for criterion is Gini, max tip is equal 3, and so on. We can also check to see the best performance score achieved by that combination by using best score, which is here 72%. Grid search can be used for other algorithms, not just decision trees. It's usually very effective, but keep in mind in some cases it can be very time consuming because it checks all combinations. So that's all for this video. Thanks for watching, and I'll see you in the next one.